Good evening, everyone. So, on behalf of the IIT Guwahati SP student chapter, I warmly welcome you all today in the BATON technical series on the topic of advanced material for solid state and conventional rechargeable batteries. We are delighted to have students, research faculty members, and professionals joining us for this session on the next generation energy storage technology. About the IIT Guwahati SP student chapter, our chapter aims to create a platform that connects the students with the industries, research, and emerging technologies in the energy sector. Through this technical series, workshops, and collaborations, we focus on bridging the gap between the academic learning and the real world energy challenges. About this Baton series, so it's basically battery application and technologies for optimized network. This initiative was done focusing on the advancing understanding in battery technology, energy storage system, and material innovation, critical to the global transitions towards electrifications and sustainable energy system. So it's my great pleasure to introduce our distinguished speaker for today's session. We are honored to have with us Professor Paul V. Braun, Director of Material Research Laboratory at the University of Illinois, Urbana-Champaign, USA. Professor Braun is globally recognized expert in advanced material and energy storage system with pioneering contributions in architectures and 3D battery materials, solid state next generation energy storage, electrochemical materials and interface engineering, scalable designs of high performance battery system. His works has significantly influenced how we design and engineer batteries for improved performance, reliability, and scalability. So with this, I would like now to invite Professor Braun to deliver his talk. Sir, we are truly honored to have you with us today. So you can start now, sir. Thank you, sir.
Oh, thank you so much. Thanks for the invitation. It's really a pleasure to talk with all of you today, and
Sure, sir.
giving me the opportunity to share some of the work of my group. I'll start with things that probably most of you know, but as way of background, we can start with what were the first batteries. These were about 250 years ago. People realized that you could create electricity by stacking dissimilar materials and putting a separator between that was wet with an electrolyte. In fact, it's very interesting that the very first Voltaic piles and the batteries we have today are actually not very different in their physics or their design. They consist of layers of anodes and cathodes, either in parallel or in series, with some sort of current collector, electrolyte, and separator. And so really what the difference is between the early Voltaic pile and where we are now is the materials. We've of course come up with materials that have much higher energy density, better power density, better manufacturing approaches, designs that will last. The early Voltaic piles tended not to be rechargeable. Of course, they didn't have generators anyway, so recharging was not much of an option. These batteries, in fact, they generated their energy through initial chemical processes. And so when you made the metals, it was the reductive metallurgy that added energy to the system. Of course, today we can do that via electricity when we recharge. Now, of course, you can make this battery at home. All you have to do is use two dissimilar metals, one of which will be partially oxidized, and then one which will undergo reduction chemistries. And if you insert that into an electrolyte, such as a lemon or a potato, you can generate a voltage. Now, of course, in today's batteries, we need to have higher energy and power density than this. But again, the fundamental physics is not much different. So if we look at where we are today, if we look, for example, at a cell phone battery, they're quite small, maybe 10 or 20 watt hours. They, of course, have to be highly reliable. The manufacturing costs have to be reasonable, but doesn't require a lot of scaling. When we really want to change the world, when we talk about changing energy on the world landscape, whether this is electric vehicles or grid storage, or other power grid management systems, or say home batteries, the batteries are much larger. They're many kilowatt hour. And the reason this is so important is that when you think about batteries, you have to be able to manufacture batteries at scale. We need to be able to make battery materials by the ton, and we have to know how to assemble them into large systems. And so that has been a major challenge. There are many, many battery chemistries in the academic literature that are not very practical. And so what's important is to think about the fundamental learnings that we obtain, and then how can we apply those learnings to large-scale systems. So we think about the fundamental physics. So how does a battery work? Well, let's start with charging a battery. When you charge a battery, what we're doing is we're moving lithium from the anode, where it is in or near a zero valent form, and moving that over into the cathode in an oxidized form. Then when we discharge the battery, we're moving it back. And of course, when we move the zero valent lithium to become +1, we have to move electrons through the external circuit. When we discharge the battery, the same thing. When we discharge it, the lithium comes out of the anode and goes back into the cathode. And as it does that, electrons have to move the opposite way. So the difference in the energy between a charged and discharged battery is really the difference between when it's charged, the lithium is primarily in the zero valent form, and when it's discharged, the lithium is predominantly in the +1 form. One of the major challenges with batteries is that the lithium is a minority component. For each lithium atom, we have 6 carbon atoms. And if the cathode is, say, lithium cobalt oxide, and we can only extract half the lithium, we have 2 cobalts, 4 oxygens, and another lithium that we don't use. And then on top of that, we have current collectors, separators, electrolyte, and many other components. So really one of the goals here is how do we minimize all of these inactive or dead weight elements? And if we can do that, then we have a system that is higher in energy density and potentially in lower in cost, because all of these other materials have real costs. In fact, one of the goals of my group is to think about how can we design batteries to be more like semiconductors. Semiconductor devices consist of multiple layers. Here, for example, is a silicon heterojunction solar cell. And these multiple layers each play a very important part. But what you'll see is that each layer is exactly built onto the underlying layer. And because these layers are so carefully controlled, you end up with high efficiencies. If we look at a lithium-ion battery, we start out with a metal current collector, and then we basically put powders on the current collectors. We squeeze the powders together. We hold them together with binder. We add in a plastic separator. In the cathode case, we apply very high pressures and we crack the material. And so by its very nature, it is not optimally designed. So what I would argue is while batteries today have active material randomly oriented, the surface termination varies, there's highly tortuous pathways and a complex structure. And finally, it's filled with a thermodynamically unstable liquid. What we'd really like to do is to eliminate all of these problems and build it so that materials are not randomly oriented, control the termination, limit the tortuosity, simplify the internal structure, and make it more thermodynamically stable. And so this led us to start thinking about what could we do as far as alternative designs, and I'll talk about the cathode here. It had been known for several decades that ceramics could be electroplated, that you could take a ceramic material, or you could form a ceramic material much the way that we form metals electrochemically. Now, the physics was a little different. In some of these cases, instead of reducing the metal, we oxidized the metal. But what workers had seen is that you could indeed grow single crystals in highly textured materials. So we applied this to think about electrodeposition. And so now in the electrodeposition, what we do is we take a dissolved metal and convert that to solid ceramic, in this case, lithium cobalt oxide. And by converting it to lithium cobalt oxide, electrochemically, we can control the tortuosity and we can control the crystal texture. And so the potential now is here for a system that contains no binder and no conductive additive, is directly growing on the current collector, and is growing with a very high degree of orientation. So what is the physics and what is the chemistry? So in the specific system that we work on, which is lithium cobalt oxide, and I'll mention a few others as we go through, we have to look at the Pourbaix diagram. The Pourbaix diagram gives us an idea of what is stable, at what potential and concentration. And what we see is that there is a stable electrochemical region of lithium cobalt oxide. And the process here is that we dissolve the cobalt oxide in a near eutectic melt of lithium and potassium hydroxide. Then we electrolyze, we oxidize the cobalt from 2+ to 3+. And when we do the oxidation, it precipitates as lithium cobalt oxide. At the counter electrode, we deposit cobalt and then produce water, which boils out of the bath. And the material that's formed is very high quality. So if we look at the specific capacity, it's near theoretical. One sees all the features you would expect to see in highly crystalline lithium cobalt oxide. When we build it into a cell, it cycles quite efficiently. So this cycles 400 times with a Coulombic efficiency of near unity. And the material as grown is nearly phase pure. So indeed, what we have is a high quality cathode material containing no binder and no conductive additive. And as I'll show in some of the subsequent slides, it's very highly oriented in a way that enhances the energy and power density. And this is just a larger view of this same now lithium cobalt oxide coated cathode. And what you can see here is that the lithium cobalt oxide is nearly dense, it's highly textured, it's binder free, and it's conductive additive free. So this is a material that eliminates some of that dead or inactive mass that I was discussing. As you can also see now, the grains are highly columnar, and these highly columnar grains provide fast pathways for electron transport and for ion transport. Because we do this electrochemically, we have additional knobs. So unlike, say, a high temperature process, we are able to vary temperature. We're able to vary the concentration and chemistry of the precursors. And what that allows us to do is control crystallography. So we can grow material so that it's highly oriented in the vertical direction and that it's highly oriented horizontal or parallel to the substrate. Now, from a rate performance, this is much preferred, the vertical orientation, because the fast ion and fast electron direct transport directions are parallel to the 003 planes. There may be reasons you want to go to various angles, and I'll discuss that briefly because it allows control of the chemomechanics, which is very important for solid-state batteries. But unlike a powder where it is random oriented, here we can control it. And you can just see over here the impact on the rate performance. When it's vertically oriented, it has very good rate performance. When it's horizontally oriented, it has very poor rate performance. And that's because here the fast transport directions are aligned perpendicular to the current collector, and here they're parallel. So we can build a phase diagram, and this gives you an idea of what will happen at different temperatures and different current densities. The blue is the region that we like the most. It has the proper orientation, but there are other cases where perhaps you want different orientations. What we see is at high temperature is it all ends up being parallel. The 003 planes are parallel to the substrate, and we would call this thermodynamic takeover. That's the lowest energy. This is a kinetically trapped orientation here in blue. So you might ask from an engineering standpoint, what is the advantage? So if one looks at a slurry cast lithium cobalt oxide cathode, When it's 50 microns thick, it has a capacity of about 2 milliamp hour per square centimeter. In the electrodeposited material, now when it's 26 microns thick, it has the same areal capacity. So the thickness is reduced by almost a factor of 2. In addition, the tortuosity is much diminished. Here, the lithium transport is all in the fast direction. Here, the lithium transport is very complex, it has to go around all of the particles. And what this does is this has a much diminished rate performance relative to the highly textured material. So for those of you that do electron microscopy, here we're using electron microscopy and specifically EBSD to determine the crystallographic orientation. By SEM, you can easily see the columnar grains. And these large columnar grains, they start at the surface actually as small polycrystalline grains, but then certain grains take over, and one achieves the high degree of orientation. If you look at a phase map, it's phase pure, so it's indeed the orthorhombic lithium cobalt oxide. And if one looks at the crystal orientation, one can see that it's predominantly oriented with the O3 planes parallel to the desired transport direction, or what we will call the 110 orientation. So the O3 planes are primarily running up and down. Because the fast transport directions are aligned this way, one can grow thick electrodes that still cycle. So capacities of 10 or even 20 milliamp hour per square centimeter. And so that means the system has much higher areal capacity and much higher volumetric energy density than can be obtained in a commercial system. It cycles quite well even when thick. These are 10, 11, and 20 milliamp hour per square centimeter, and they've now cycled about 100 times. And actually what starts to fail is the separator, not the active material. So here's just some examples now of going thicker. Again, electrochemistry has the advantage. If you tried to cast an electrode this thick by slurry, what would happen is it will crack as the solvent dries, or the tortuosity will impact performance. Here, this is now 120 microns thick. And so this has similar power as a commercial 3 to 4 milliamp hour per square centimeter cathode, even though it's 50% thicker and has 2 times the loading. So it has over 7 milliamp hour per square centimeter. And so that's one of the advantages, that we have this very good transport because of the high degree of orientation. We really did this only for fun. This is a ultra thick cathode. This cathode here is 730 microns thick. It does cycle. It cycles rather slowly, to be honest. You can see these lines because we had to keep adding cobalt into the bath. But this system shows that indeed by electroplating, you can grow ultra thick materials, unlike what would be possible in a slurry. If this was a slurry, it would have cracked and it would be disconnected and there would be a lot of dead material. If we continue to look at the thick material, the rate performance continues to be good. And we compare that with what's in the literature, we can see that compared to the literature at any given capacity, the maximum current density is much higher. So again, I think this shows the importance of orienting material in the vertical direction. And a major part of that is because of the reduction of tortuosity. Remember that when you take a powder, when you pack a powder, it will tend to be quite tortuous. The tortuosity can be 2 or 3. In some cases, it can even be up above 7 or 8, for example, in graphite, because of the flake-like nature. And so what this does is this provides much better transport because the tortuosity is close to 1. And I'll show that here in some of the images. And so these are now SEM images of the electroplated cobalt oxide. You can see these sort of cracks or vias We put those in intentionally, and they provide ways for electrolyte to come deep within the structure. They run almost perfectly in the vertical direction. And so if you look at a cross section here, you can see that the tortuosity is only on the order of 1.2 as compared to commercial electrodes, which have tortuosities of 2 to 5. And so because we have a much lower tortuosity, we're able to make thick electrodes that cycle well. So let's look a little bit more at the crystallographic structure of the material, because this is important not only for tortuosity, but for chemomechanics. So in lithium cobalt oxide, and in fact in most cathode materials, as it charges and discharges, the material expands and contracts. And so if I have a material that's expanding and contracting, and the grains are polycrystalline and randomly oriented, you will start to drive cracks in the material. On the other hand, if all the grains have almost the identical orientation, when I cycle it, it's all expanding and contracting the same way, and so there is very little in the way of crack damage or other defects in the structure. And so here we look, this is just a classic powder, the SEM when it's pristine, and after cycling, you can see the cracking. When we do a phase map, it is pure. This is what expected. These are commercial lithium cobalt oxide powders. And when we do an inverse pole figure, what we can see is, for example, the crack here, it occurred between, even though this was a single particle, it had 2 grains, and one grain cycled differently than the other, and that led to cracking along the interface. And if we look at that, you can look at grain size, and so in fact we see that there are size effects to the cracking, and most important, we can map out the grain boundary types, and the cracking here is occurring along a high-angle grain boundary. High-angle grain boundaries have the lowest cohesion energy and thus are the most susceptible to cracking. The difference is that if I make powders, I can't control it. When I do the electrodeposition, I can engineer all of the grain boundaries. And because I can engineer it, what I will show you is I can control the mechanics, which means I can control the cracking. And so this is another advantage of growing the electrodes via an electrochemical approach versus the randomly oriented material. And so if we look at SEM images after cycling, one sees that there is cracking again. You see lots of cracks running through this material. When we look at the grain orientation, you can see that the cracks occurred here where the grains had different orientations, because one grain was trying to expand one way, the other grain was trying to expand and contract the other way, and so it cracked. When we go ahead and do this in our electrodeposited, because the grains all have basically the same orientation, that means we have a lot of low angle and coincident site lattice boundaries, and those boundaries have virtually no cracking present. And so we did a larger statistical analysis of cracking and misorientation angle. And what we see is that cracking occurs only in these high angle grain boundaries. That's the pink regions here. On the other hand, when we electrodeposit, you see that there's virtually no high angle grain boundaries, and the grain boundaries are clustered between being the low angle grain boundaries and coincidence site lattice boundaries. And so these are quite stable. And these boundaries here in between are not present the way they are in the slurry cast system. And the net effect is a dramatic reduction in cracking. And because of that, it cycles quite well. If we look at the grain boundary engineered cathode, it has a higher areal capacity because it doesn't have dead material. And so both from an areal and volumetric, it's substantially better. And these are cycled at C/3 from 2.6 to 4.1 volts. So the slurries, which are highly engineered as commercial material, our simple electrodeposited materials, which do not have any of that surface treatment, has similar cycling stability and 1.5 times the energy. If we look in the detail of the electrochemical performance, we can see that the Wartburg resistance is very similar, but the big change is in the area's specific resistance. And so the grain boundary engineered material has a very low interfacial resistance, while the slurry cast one, the CEI resistance continues to grow. And it continues to grow because as it cracks, it generates new surface. The new surface generates CEI, and that CEI probably then leads to additional cracking. And so from a stability standpoint, minimizing that cracking leads to longer stability or better stability. Okay, let's talk about a few other chemistries here, and then we'll go discuss some about the solid state systems. So what I've talked to you so far about is lithium cobalt oxide. A few years ago, we published a paper on other sodium systems, and so we made the sodium cobalt oxide, sodium manganese oxide, sodium nickel oxide, and sodium iron oxide. These are interesting because of the interest in using sodium in place of lithium. So the cost of sodium, of course, is near zero. Lithium is more expensive. There may be reasons that sodium batteries are more stable. They tend not to have as good a kinetics, but still are of interest. Overall, the system looks quite similar. Here, we're just using a bath of sodium hydroxide and cesium oxide, so a little bit different bath chemistry, but the same concept. And the Porbet diagrams are shown here. And so indeed, there is a stable region of sodium cobalt oxide, sodium manganese oxide. The electrochemistry is a little bit more complicated. And so when you cycle, for example, there are multiple peaks, there's some irreversible phase transitions. But again, what we see here is that indeed these materials cycle and can be electrochemically deposited. The sodium nickel and sodium iron oxide are a little bit more complicated. There actually is no thermodynamic stability region for the sodium nickel oxide. And so while we can grow it, the Coulombic efficiency is quite low. There's a lot of oxygen evolution during plating. The sodium iron oxide will grow. It turns out it doesn't grow very well. Also, the reaction is more complex. It involves an unstable intermediate, which then has to collapse to form the sodium iron oxide. If we just look a little bit about the sodium cobalt oxide, because we can directly compare this to our lithium cobalt oxide, it's quite similar. It's primarily O3 with a small amount of O prime 3. It doesn't grow quite as dense, although we haven't worked as hard. You can see that there's these platelets. The O3 planes make up the faces of the platelets pretty much as expected. And giving examples of the cycling, here is the sodium cobalt oxide. It does fade and then becomes quite stable. Coulombic efficiency is reasonably good. The sodium manganese oxide has sort of a slow and continuous fade due to phase changes. So I would argue that if the sodium systems are of interest, there's still some additional work to do. Okay, so one of the things about most commercial cathode materials is that they have surface treatments. And so we were really interested in how could we treat our materials? Could we come up with alternative treatments that are, say, more attractive? Could we take advantage of the plated materials? And we started to consider plasma treatments. And so this, of course, is a plasma globe. And when you touch it with your finger, you're locally changing the capacitance. And so the filaments tend to go to those regions. Plasmas are regularly used to modify surfaces. This is used in the semiconductor industry all the time. And basically, a plasma is a very high energy ionized species, and those ionized species have sufficient energies that they can react. And so that's what makes them attractive to create ultra thin layers, for example, in a semiconductor process. So we're specifically interested in modifying the cathode. And so we start with lithium cobalt oxide. And what we discovered is that we can use a plasma method to introduce a small amount of aluminum and fluorine. And what that does is that creates a stable surface. And so the surface transforms from layered to rock salt. It becomes a disordered rock salt. And the combination of aluminum and fluorine in that layer increases the cycling stability significantly. One of the advantages is if you had a normal electrode, which contains carbon and binder, the plasma could damage that. Here we do observe no damage to the material due to the plasma. Also, the plasma is very useful to modify the surface. And of course, our plated materials are primarily a top surface that is exposed. And so if we look in the electron microscopy, what the plasma does is it actually converts it from layered to a very thin layer of disordered rock salt. And this disordered rock salt layer is highly stable under the electrochemical conditions of cycling. To understand what the surface is, we did a lot of XPS. I won't go into all the details, but what it does is it modifies the surface, introducing various cobalt fluoride phases, lithium fluoride, and aluminum fluoride. So this gradient disordered rock salt contains a mixture of cobalt, lithium, and aluminum in fluorides as well as oxides. And so it's a complex structure because it contains fluorine and oxygen on the anion sites and cobalt, lithium, and aluminum on cation sites. And we observed a dramatic improvement. So if we take a very good electrolyte and then go to high voltage, after 250 cycles, only 13% capacity remains. If we do the surface treatment, 55% capacity retains after 500 cycles and almost 70% after 250. And when we take a electrolyte which is not improved, so this is an additive free, the conventional material basically fails in 50 cycles, while this is still has substantial capacity after 500 cycles. And we can see just the difference here. This is the first, the 50th, and this 250th cycle. Here's the first, the 50th, and there's the 250th here. So by 250 cycles, it's completely faded. So what I had shown you so far was treatment of lithium cobalt oxide. Lithium cobalt oxide is interesting. It's used in a lot of handheld devices, but it's a little bit expensive. And so NMC is a very popular system. NMC is found in many automotive batteries in particular. And what we see is that the plasma treatment also provides substantial improvement of NMC. And so that's very significant because NMC modification is probably more technologically important than the LCO. And this is actually a side view of the chamber, and this sort of reddish glow is indicative of lithium. And so this reddish glow implies that some lithium is probably being removed from the structure as the aluminum and fluorine is being inserted into the structure. Okay, so what I've talked about so far is primarily liquid systems. I want to start talking about solid state systems. So solid state batteries have been proposed to be the future now for quite some time. In a conventional battery, you have graphite, a liquid electrolyte, separator, and a cathode. In a solid state battery, the graphite is reduced with lithium metal, which potentially improves the energy density because the graphite, of course, carries 6 carbon atoms for every lithium. Here you get rid of the carbon atoms. Hopefully we can use a solid state electrolyte, which is much thinner, and now the positive electrolyte. So solid-state batteries remain very much a research topic, but have the potential for higher energy density and longer cycle life. And so what we wanted to see is, would the plasma process provide advantages? And indeed, we see it does. So if we make a battery here, the key to look at is it's just pristine LCO. So this is our electroplated LCO, and it is facing lithium indium chloride. And this is the one with the plasma treatment on the surface with lithium indium chloride. And then finally, here's one with LPSC. LPSC is not thermodynamically stable, so without treatment, it simply dies. And what we see is that after the treatment, if we don't treat the cell, it dies within 20 cycles. When we do treat the cell, it cycles out past 500 cycles. And this is very aggressive. This is up to 4.5 volts versus lithium. And what we see is in pristine LCO, the resistances are increasing dramatically. While if it's treated by EAIS, you see that the resistances increase only very slowly. And so indeed, this shows that in a solid state design, this surface treatment is even more important because it is that surface layer. There's an interface between the solid electrolyte and the cathode, and all of our treatment is occurring exactly at the surface, which provides a much improved cycle life. And in fact, even at high temperatures, it's quite stable. So this is sort of an aggressive treatment. And what we see is that with pristine material, again, it fades, where using the material that has been surface treated, there's almost no fade. So there's a lot of failure modes. The only one I've shown you there is interfacial reaction. So we've covered that, but there's also a lot of issues with volume changing and cracking. And so this goes back to this discussion about chemomechanics. If I take lithium cobalt oxide, as I cycle it, there is strain. So the A-axis, it decreases as I pull out the lithium. So that's moving to the left is removing the lithium. The A-axis decreases. The C-axis, as I remove the lithium, it expands. And so this crystal is trying to change shape. And when it changes shape, it, of course, builds up a lot of interfacial stress. And so what we found is that we could actually crow the crystal. So if we have it this way, there's going to be an expansion and contraction. But if we orient the crystal at just the right angle, we can create a system where the net strain is very close to zero. And what that means is now that the strain that the current collector is feeling, and that the separator is feeling, or in this case, the solid state electrolyte is feeling, and the anode is feeling, and the anode current collector is feeling, we can control all those strains to make them very small, or we can make them positive or negative. And so what the advantage is that if you don't control the strain, here is pressure versus cycling. If I take a cell and I block it. So what's happening is that the cathode is expanding and contracting, and that's leading to pressure changes. Well, when those pressures become negative or zero, that means material is moving apart and voids can form. And so if we want to minimize voiding, we want to minimize the point at which the system is being pulled apart as the cathode shrinks. And so here you can see that the pressure is about 100 kPa, and it is positive with state of charge. Here, by varying the orientation, we can see the pressure is only about 30 kPa, and it is negative with state of charge. So here we've completely switched it from a system that is expanding during charging to contracting during charging. And we want it to contract during charge because when you're charging, the anode is getting bigger. So you want the cathode to get smaller. And during discharge, the cathode's getting bigger. So you want the anode to get smaller. So this matches the stresses on the anode and the cathode. Here, they're going to pull themselves apart. And so that shows up during discharge as voiding. And so if we make a battery with a very low stack pressure, so we don't push it together very hard, what you see is as you discharge, if the stresses are opposing, you have voids. On the other hand, when the stresses are complementary, voiding is prevented. And so here, if we look at 1 MPa stack pressure, if we design it so that the stresses oppose, after about 1.5 milliamp per square centimeter, there is voiding. On the other hand, we can go to much higher currents without voiding when the stresses are complementary. And this is important. While it disappears at 5 MPa, remember 5 MPa is 50 atmosphere. And so if I'm going to make a practical battery, I want to be working down here. And so what this means is that at very low stack pressures, which are practical, you can minimize battery failure by controlling the chemomechanics of the anode and the cathode. And so basically what is happening is at low stack pressure, when I'm charging the battery, the lithium's getting bigger and the cathode is shrinking, so that the two sides are working together. During discharge, as the lithium gets smaller, the cathode gets bigger. On the other hand, if I don't control the stresses, they fight each other. During charge, they're compressing. That's probably okay. But then during discharge, the cathode is pulling one way and the lithium's pulling the other way, and voids form. And these voids lead to failure. And once you have a void, in the next cycle, you're likely to have a dendrite. So I think that the controlling the chemomechanics both allows you to do a high current density discharge, which is high power, that's important, and it allows you to do high current charging without having dendrites because you don't create those dendrite initiation sites. And here just shows we made a simple cell. This one failed. The reason there's only 5 cycles is because after that, the capacity went basically to 0. You can see it falling here. This is the negative LCO, and it continues to cycle. And when we cycle this under a little bit less aggressive conditions, you can see here that we have 86% capacity retention after 100 cycles. We can do this kind of strain engineering for other systems like NMC, and we see indeed that by doing strain engineering, we can get very good cycling, much as we see in the LCO system. And so I think this is a generic phenomena that strain engineering in solid-state batteries will enhance cycling performance, and any solid-state batteries should be made accounting for the chemomechanics of both the anode and the cathode. And what we see here, this is sort of, I would say, our best cell to date. And so this is cycled to 4.5 volts, so very high voltage. And what we see here is that there is virtually no fade after 1,000 cycles in a solid state at 1 MPa. And that's very significant because that means that you can start thinking about a practical system. And this is made with the NMC versus LIC. We have not combined this with some of the other approaches to improve the batteries. And so I think we'll get even better performance over time. Okay, with that, I'd like to conclude. I'm happy to take questions for a little while. Hopefully I've shown you the opportunity for electrodepositing of cathodes, how electrodeposition provides control of mesostructure, how we can control the surface crystallography and the cathode chemomechanics, and how the cathode chemomechanics, control of that, minimizes void formation at low and practical important stack pressures. And here's just a picture showing the crystallographic orientation, the EBSD. Below that is a map of the sizes. So there's a lot of data that we can extract from this. And then finally, showing the tortuosity that is much reduced in the system compared to a slurry. Just want to point out a few people that contributed extensively to the work here. Olga Patra led all of the grain structure work. Adrian and our collaborator, Ella Fertikin, did all of the DFT and helping us understand the surface chemistries. Patrick Kwan did some of the higher temperature work. Sahid Muradi looked at the pressure system, being able to control pressure. And then also collaborators, Daniel Shoemaker, Ben Zahiri, and Jim Zhuo, who worked on various aspects, in particular Ben Zahiri, who's a research professor that I work very closely with here at the University of Illinois. So with this, I'll stop and I'll be happy to answer any questions. Thank you.
Hello?
Yes.
Yeah. So good morning to you, sir, for your time, sorry. And I had a couple of questions from the, I hope this is okay that I am speaking rather than putting in the question in the comments.
Oh, no, this is great.
Okay, cool. So one of the sections that I work in mostly supercapacitors rather than batteries. And currently I'm working with metal oxides, metal oxides as well as some mixing material with the 211 family. So we generally create our cathodes with a little bit of additive binder like PVDF, and then with metal oxides you have this possibility of semiconductor behavior, so you have to put in some amount of conductive material as well, let's say CNT or Super P. So my question was that this electro-deposition technique, it does provide a very good alternative, since you do not really require a conductive material or rather additive as well for a binder. But how do we actually, my question was that how do you ensure a vertical deposition rather than a horizontal one, as you already showed in the results that the horizontal deposition does reduce the capacity, and I believe that the layer stacking on top of one another would eventually cause the capacitance to decrease, right? Restacking of the material would cause the capacitance of the material to decrease. So how do you ensure that vertical deposition?
Yeah, no, that's a great question. We've developed processing phase diagrams. So what we did is we explored the effect of precursor concentration, electrolyte chemistry, temperature, and current density. And from this, we can find regions where the material predominantly grows with the vertical orientation, and then there's other regions where it predominantly grows with the horizontal.
Okay.
Usually the vertical orientation grows under higher current density and lower temperature, and the horizontal is closer to what we would call thermodynamic control. And so in those systems, it tends to grow with the layers near parallel to the surface.
Okay, so I guess that the same theory extends towards the part of chemomechanics that you included later on.
Yes, but so what we do is we use our control. So if we know we want to be at an angle, there's a region of phase space or processing space that predominantly grows the material at an angle. So it's really, once we know the phase diagram, then we can tune the processing conditions to get the desired crystal orientation.
Okay. Again, you have another question I have, sir, is that you have extensively talked about the cycle life of the materials. And so, I mean, I've not worked as such with electrochemical depositions, but since you had shown the results of, like, let's say, including a binder for slurry-based as compared to electrochemical deposition, and that is exceedingly larger cycle life. So that was one of my questions in the initial part of the talk, but like later on when you proved it to be when you showed the results to be more stable for the electrochemical deposition, that question got resolved. So based on the economic standpoint or the economic study of this process right now, as you had in the start of the talk, you had talked about the creating this material in tons and tons, right, for it to be viable for the battery system. So would that not like creating certain conditions for vertical deposition, as you said, with lower temperature and a higher rate of higher energy density? So would that not require a decent amount of initial capital expenditure for creating the systems? And is there any economic study done on that?
So we're working with a company, Xerion, who's doing those studies. They have built a pilot scale system. What the advantage is, you remove many of the steps. So you no longer need a drying oven. So all of the steps are performed really in one machine. So while the one machine you need is probably more expensive than each individual cathode machine, the processing, it can be done roll to roll. So it's still compatible with larger scale manufacturing. And you don't have to do a lot of the pre-treatment. So we start with cobalt oxide. Conventional materials, of course, have to start with the organic salts. Those salts are then calcined and ground, mixed with binder, conductive additive, and solvent. There's no solvent in the process here, so that means you have less solvent control. So we believe that the overall capex of the plating approach will be lower than the total capex for a conventional slurry system.
Okay. Yeah, sir. And one last question from me. I'm really sorry I'm taking so much of the time.
Please.
So one last question from me is that you talked about some of the people who have helped out with the computational side of your studies. So I predominantly work with quantum espresso for density functional theory studies, as well as some amount of thermal stability studies as well at like a picosecond scale for a decent system. So I just wanted to know that could you reveal like what kind of studies were performed on it on the system, and do you also move towards the P2N type of studies that are more industrial based battery system studies where you are?
So we primarily work with Professor Ella Fertiken, who is an expert in DFT, and her group has looked both at the plasma treatment, so the top surface, as well as the effect of crystallographic orientation. So the difference in the interaction of, say, 003 versus a 110 face. And so she's looked, for example, at the shared electron density at those interfaces, the bond strength of those interfaces, and then via DFT, looking at the disordered rock salt, some energy minimizations to understand what phases are likely. With DFT, we've done a lot of work as looking at sort of what species. So, right now we're looking at aluminum. Of course, there's many potential compounds. We look at fluorine. So that allows us to better survey the periodic table instead of doing each experiment. We don't do much of our own work on the more practical calculations. We work with Professor Partha Mukherjee at Purdue University, who does some of those. I didn't include his work here, but he's worked with us on some of the more practical calculations. I do think simulation in theory is very important here because the chemical space is large. And if we have to do every experiment, it's unlikely to, it's going to take too long to do every single possible experiment.
Especially when we talk about the different composition when we go into NMC side.
Absolutely, yes.
Okay.
So,
Yeah, that's all questions from my side, sir.
okay, anyone would like to ask any other question? Okay, so we will be like ending today's session. I would like to express our sincere gratitude to Professor Braun for sharing his valuable insight with us. Special thanks to the organizing team of IIT Guwahati SP student chapter for their efforts in making this event possible. And with this, we conclude today's session. Thank you, sir, for all, and we look forward to seeing you in our upcoming any other initiatives. Like, thank you for having these sessions.
No, thank you for the invitation, and look forward. If I ever meet some of you, please remind me that we first met at the presentation here. And best of luck in your studies.
Yes, thank you, sir. So if you like anytime, like if you visit India, if right, you can just like have a interaction in Guwahati, right? Okay, sir.
Absolutely, thank you.
Thank you, sir.